Hi, everybody. We are back to pick up our discussion regarding hypothesis testing. The basic idea was that we had some claim about the population mean. Here in this example, our belief is that the mean age of a gamer is 15 years. And then we go ahead and take a look at the entire process of hypothesis testing, which again starts with us identifying the relevant population of gamers. And then we select some sample randomly from that population. So we have now a sample of gamers and we look at the average ages of our sample. And in this sample, it turns out the mean age is 35. And the idea behind hypothesis testing involves asking the question, is it likely to observe a mean of 35 from the sample if the population mean was actually 15? And if the answer is no, this is not likely, then observing the sample mean of 35 means our presumption that the population mean was much lower is not correct, and we would want to go ahead and reject the null hypothesis. So the idea we looked at, again, diagrammatically, is the following. We saw a sample mean out here at 35 years of age, and if we're assuming that the true population mean was 15 under the null hypothesis, right, if that were true, okay, then what we need to think about is how far away does this value need to be from the mean in order for us to say that our presumption, right, our assumption here, our null hypothesis under the status quo should be rejected? Okay, so we're going to formalize that idea in just a moment. We'll go through a couple examples in the next video segment, but for now, I want to talk a little bit about the types of errors you can make in decision making. There's something known as a type 1 error, which actually, when we run the hypothesis test, we'll be able to control how much of that we're willing to accept, our tolerance for the type 1 error as the practitioner. And the type 1 error is really related to the event where we reject a true null hypothesis. Okay, so this is kind of like a false positive here. The researcher concludes there is some statistically significant relationship that exists when in fact there isn't. Okay, so the probability of observing this type 1 error, we've actually seen this before. We call this alpha. This is our level of significance alpha. And this is the probability we reject the null hypothesis by mistake, given that the null hypothesis is actually true. And again, this is the level of significance of the test that we're going to be using. And this is set by researchers in advance of performing a test. So for example, if we were using a level of significance of 5%, that means we would expect to commit a type 1 error about 5 out of 100 times running the particular hypothesis test from the resampling process. Okay, so that alpha value is pretty much the same way we were interpreting it with a confidence interval. It has to do with a tail probability here, and the researcher is going to be choosing what the acceptable level of alpha is. Unfortunately, there are some pretty standard levels that we like to use. We typically set alpha at 1%, 5%, or 10%, corresponding to the 99th percentile, the 99th percent level of confidence, the 95% level of confidence, and the 90% level of confidence that we had seen prior in our unit on interval estimation. So type 1 error, we're associating that with alpha. It is the probability of committing essentially a false positive. Type 2 error is a situation where we fail to reject a null hypothesis when the null hypothesis is actually wrong. Okay, so in some sense, this is a false negative, right? The researcher concludes that there is some relationship that does not exist when the evidence suggests that it does. And we use the Greek letter beta to denote the rate at which we would commit a type 2 error in observing a false positive. And again, this is a situation where we fail to reject the null hypothesis, given that the null hypothesis is actually false. In other stats course, you may hear a term referred to known as the power of a test. And this is 1 minus the likelihood of committing a type 2 error. So that's the probability that a false hypothesis will be correctly rejected is the way to think about that. And if you have larger sample sizes, that typically leads to increased, or rather a reduction in type 2 error, which means we have increased power in our test. Now, I've kind of broken down this grid here to think about the context of type 1 and type 2 errors as how they would relate to a jury trial. And we've discussed this idea before, where in the jury trial, the null hypothesis is that you're innocent until we've provided enough evidence against that, at which point we could reject that hypothesis in favor of guilt. Okay, so if we're thinking about a situation where the null hypothesis is true, and we correctly do not reject the null hypothesis, this is a situation where we do not make that type 1 error. Okay, so that is us correctly not rejecting a null hypothesis. The other situation where we could be correct here, okay, is the null hypothesis could be false. They could be guilty. And we can accurately describe them as guilty. So that means the null hypothesis is false. We're in the right column, and we correctly reject that. That happens with probability 1 minus beta, and that is us not committing a type 2 error. Hey, what's the likelihood of committing a type 1 error? Where does that fall on this diagram? Well, a type 1 error involves the null hypothesis being true, but us rejecting it by mistake. So that bottom left box there is us committing a type 1 error, which happens alpha% of the time in a hypothesis test. And then that leaves no mystery to the type 2 error, which again is when the null hypothesis is false and we fail to reject it. And that occurs with probability beta. Now, the relationship between these two types of errors, this may be hard to see, but it turns out type 1 and type 2 errors cannot happen at the same time. Okay? Meaning type 1 error, again, can only occur if the null hypothesis is true. A type 2 error can only occur if the null hypothesis is false. Okay? And it turns out that increasing one of them reduces the other. If I'm accepting more type 1 error, if I allow alpha to be bigger, that allows me to reduce the frequency of me committing a type 2 error, as you can somewhat see here implied by this teeter-totter or seesaw diagram. Increasing alpha reduces beta, and vice versa. They are inversely related to each other. Okay, now, what's an acceptable level for either really depends on the nature of the narrative we're dealing with here. Sometimes, a false positive can be very costly. Like, for example, if we accidentally let somebody into CIA headquarters when they scan their thumbprint at the door or their handprint, if we accidentally commit a false positive, letting them in when we really shouldn't have, that's pretty costly. But if we committed a false positive, let's say at the grocery store to check out at Vons, where maybe we mistakenly gave somebody a discount where we shouldn't have, there the cost of that type 1 error is actually much lower. So, the choice of the error, or the cost rather, okay, that you're willing to accept really depends on the narrative here. Okay, if the cost of rejecting the maintained hypothesis is very high, if you accidentally reject, okay, then you want to choose a smaller type 1 error so that it happens less often, right, where we're rejecting a true null hypothesis. Okay, in a criminal trial, this would be the equivalent of convicting an innocent person, right? They're not innocent, but we reject the null hypothesis that they're not innocent in favor of guilt. If that's the case, I would argue that's a pretty serious type 1 error in terms of the cost, right? Nothing compared to accidentally giving someone a discount who shouldn't have gotten that discount. Conversely, if you choose a smaller type 2 error, you would want to do this when you have an interest in changing the status quo. So again, that type 2 error is the failure to reject a false null hypothesis. And in the context of our legal quandary, this is a situation where a guilty defendant is acquitted by mistake. Okay, so you can think, which is worse? Is it worse to acquit a guilty defendant, or is it worse to convict an innocent defendant? It probably depends on the scope of the charges, but this is the idea that you want to think about in terms of negotiating the trade-offs between the type 1 error and the type 2 error. Now, consider the following situation where we're jumping out of an airplane and the null hypothesis is that the parachute works. The alternative hypothesis is that the parachute doesn't. And we want to decide here whether a type 1 error or a type 2 error will be more serious in this situation. So you might want to think about that for a moment. Okay, and hopefully you're thinking, well, the worst situation here is if the parachute did not work and I thought it did. If the parachute works and I think it doesn't, then I might not go skydiving, no big deal. Some cost there, but no big deal. But if I think the parachute, or sorry, if the parachute does not work and I think it does, right? So if the alternate hypothesis is true, but I don't think it is, okay, then the type 2 error is way more serious in this situation. I may die or may be seriously hurt. If I commit the type 1 error, not a big deal. Parachute works, but I think it doesn't. What do? I don't skydive, right? But I'm not killing myself. Let's look at another situation here. Null hypothesis is the shirt is washable. Okay, alternative, or sorry, the null is the shirt is not washable. The alternative is the shirt is washable. And we want to think about what is the more serious cost here. Okay, and if the null hypothesis is true, the shirt is not washable, but I think it is. I get that wrong and I commit a type 1 error, then I ruin my shirt. But if the shirt is washable, but I'm not sure and I think it's not, so I don't wash it, then I just have a stinky shirt, but I didn't ruin the shirt. So in this example, the type 1 error is actually the more serious error to commit. Okay, so I mentioned before that level of significance alpha, this is related to the probability, really it actually is the probability of making a type 1 error. And for our hypothesis test, this is going to define essentially how we're going to measure how far away from our hypothesis under the null is far enough to where we can say that we have enough evidence to reject that null. Okay, so the level of significance alpha, this is going to determine for us the rejection region in the sampling distribution. And again, typical values that I mentioned before are 1%, 5%, and 10%, so you don't have to worry about going to that normal table and looking for every possible value of alpha. Okay, we're going to use pretty much one of these 3 values, pretty standard amongst practitioners. And this is chosen by the researcher before sampling. So what we're doing here is we're going to lock in at the beginning how much of that type 1 error we are willing to accept. Okay? How much of that type 1 error are we willing to accept? And this is going to define for us what the critical value thresholds are for our hypothesis test. Let's go ahead and take a look at the critical value approach here. There are 3 general types of hypotheses tests we can think about running. One of them is known as the lower-tailed test. So let's generically assume here that our null hypothesis was that mu is at least 3. That is what we're assuming is the status quo. The alternative hypothesis, that's what we're looking for evidence to support, right, against the null hypothesis here. And that alternative hypothesis is then mu is smaller than 3. So we're looking for a sample data that is very small relative to 3. Okay? And if we set our acceptable level of type 1 error alpha, that alpha determines how far to the left we need to be relative to the mean in order to reject, to fall in this rejection region where we can say, hey, we're far enough out in the tail that our presumption under the mean, this null hypothesis, is not reasonable. We thought mu was pretty big, bigger than or equal to 3, but we're getting data that suggests it's actually way smaller. How small is small enough here? Well, it's defined by this critical z-value threshold, which we're going to determine from using the standard normal table by utilizing the value alpha in that tail probability. Okay, the other situation we could wind up with is a situation where we're trying to actually look for data that is very large relative to the null hypothesis. And this would be defined in an upper tail test here, where now the null hypothesis says, hey, we think mu is pretty small. It's less than or equal to 3. If mu is small, if that's our presumption, our assumption here under the null, okay, then the evidence we're looking for against that to violate the null, right? That swan, that's not white. Okay, we're looking for evidence that gives us a very high value of mu. So we're looking for sample data that's really large in this situation that would put us in the upper tail of that sampling distribution. So again, alpha is going to define for us this z-value threshold above which we could say, hey, we're too far away from where we think we are hypothesized at the center of the distribution, and we would then be able to reject the null hypothesis in an upper-tailed test. Okay, the last case we could wind up in is the two-tailed test, and I'm going to argue later on that this is very, very closely related to what we had done when we constructed confidence intervals. When we run a two-tailed test, now we're considering the hypothesis under the null that mu is equal to a particular value. Okay, so how do we disprove that? Well, we have to show significant evidence that mu is not equal to 3 in either direction, either the low direction or the high direction. And in this case, we take alpha, we break it in half, and we allow half of alpha, half our significance level, to define these upper and lower tail probabilities that denote the upper tail rejection and lower tail rejection regions under the critical value approach to hypothesis testing. Okay, I want to conclude here by just taking a look at type 1 and type 2 errors diagrammatically as they relate to an upper tailed test specifically. And here is kind of how we can think about this. If the null hypothesis is true, and let's suppose we observe a sample value right here. And it says any mean, that is our sample value. So then we're assuming the null hypothesis is true. There's our sample value. Okay, or maybe our threshold value that we're saying denotes the level of type 1 error. And if the null hypothesis is true, that red region denotes the probability of observing something more extreme than where my mouse cursor is currently laser on that slide. Okay, conversely, if the null hypothesis is wrong, meaning that alternative hypothesis is maybe the description of the truth, then the blue region to the left of that dividing line is going to show us the likelihood we would accidentally not reject the null hypothesis, even though the alternative is the correct distribution. So that is where I'd like to leave off on this segment. We're going to pick back up, going through some examples of all three cases, lower tail, upper tail, and two-tailed test. Stay tuned for more.